Assalamualaikum. Simple single phase induction motors suffer from two problems. Firstly, these single phase induction motors are not self-starting, and secondly, the induced torque in these motors is pulsating in magnitude, and therefore there are vibrations in such kind of single phase induction motor. So how to resolve these two problems? We shall discuss these solutions in today's lecture. There are three possible solutions which are most commonly utilized. We shall talk about each of them one by one. So how does this simple single phase induction motor work? The rotor of this induction motor is similar to the rotor for a three-phase induction motor. It is cage rotor with the conducting bars placed on the cylindrical rotor. These conducting bars are shorted at both ends, front end and back end. On the stator, we have a single phase windings, and when current is supplied to these single phase windings, stator magnetic field is produced. This magnetic field is not rotating, it is stationary. However, its magnitude is pulsating with the sinusoidal currents which are flowing in these stator windings. So in the last lecture we learned that this pulsating magnetic field can be decomposed into two flux density vectors. One vector which is rotating in clockwise direction, and another flux density vector which is rotating in counterclockwise direction. And this single phase induction motor responds to both of these components. That is, the overall torque speed characteristics of this single phase induction motor are the torque speed is the superposition of torque speed characteristics due to the component which is rotating in clockwise direction and due to the component which is rotating in counterclockwise direction. So the torque speed characteristics of this single phase induction motor, these are given by this graph. From these torque speed characteristics, we see that if this speed of the rotor is 0, that is, this rotor is stationary, induced torque is 0. However, if we give an initial push to this rotor so that it gives a certain speed, then induced torque becomes non-zero, and therefore this rotor starts rotating. So there is a problem, that is, this motor is not self-starting because the torque corresponding to 0 speed, induced torque is 0. And secondly, since this magnitude of Bs is pulsating, so induced torque is also not uniform, that produces vibrations. So here are three popular solutions. We can use split phase windings, we can also use capacitor type windings, and we can also use shaded stator poles. We start our discussion with this solution, that is capacitor type windings. With this arrangement, what we do is, in addition to these main windings on the stator, we add auxiliary windings on the stator as well. These are placed, the auxiliary windings are placed at 90 degrees to the main windings. So we have main windings on the stator and we have auxiliary windings on the stator. Both of these windings are supplied with the same single phase supply. However, in one winding, that is in the auxiliary winding, we insert a capacitor. So if we look at the electrical connections of these windings, that is given by this diagram, we have main windings, and there is a resistance of main windings and inductive reactance of main windings. So this is denoted by Rm and Jxm. So this is just to show the electrical connections. Physical placement, you know, this is a coil with multiple turns placed on the stator. Here is one side of this coil, another side of this coil, and at the back end these sides are shorted, and at the front end you are getting two wires out of this coil, and those two ends are over here. Similarly, for auxiliary windings, we have resistance of auxiliary windings and inductive reactance of auxiliary windings, denoted by RA and JXA. Both these windings are supplied with the same voltage source, AC voltage source, single phase. So here this is connection VAC. We apply AC voltage, and in series with this winding we append a capacitor. And here is a capacitor. Here is a switch which can be opened or closed. So there is a rotor as well. So why do we need to show this rotor in this diagram, in this electrical connection? Because the currents in these windings, that is not only dependent upon the voltage but also upon this rotor, because there is an interaction between these coils and the windings on the rotor. Therefore, we have to show this rotor in electrical circuit. Due to this current, due to this voltage, current Im flows in these windings, and current Ia flows in this winding. Again, the point to emphasize is that this diagram shows the electrical connections. You already know how these coils are placed. This coil is placed over here, and this auxiliary windings, these are placed over here. If I sketch the phasor diagram for this situation, here we have we take the voltage as a reference, and the current in main windings. This is inductive load, so current will lag the applied voltage. So Im will lag this voltage VAC by a certain angle. This is Im. What about Ia? Whether it will lag this voltage or lead this voltage if, for example, this switch is closed. So it depends upon the capacitance of this capacitor. So this capacitance is adjusted such that this current will lead this current by an angle of 90 degrees. We can adjust this capacitance. So this is adjusted such that this current will lead this current by an angle of 90 degrees. So if I sketch these currents in time domain, we have this situation. Omega t, we have current Ia, sinusoidal current. This is because we have applied sinusoidal voltage. And this current Im lags Ia by an angle of 90 degrees. This current is Ia, and this current is Im. This resistance, capacitive reactance, these are adjusted such that this current Ia will lead this current Im by an angle of 90 degrees. So due to this current in these windings, there will be a flux density vector Bs, which is shown over here, and let's now write it by Bm, the flux density vector due to main windings. And likewise, due to these coils, there will be flux density vector with this direction, current entering from here, leaving from here, so this direction, BA. What will be the magnitude of Bm and BA? Magnitude of Bm will be proportional to Im, because mmf is equal to N into If. So this flux density will be proportional to mmf. So therefore, these due to these two currents, there will be two flux density vectors. The direction of these flux density vectors is indicated in this diagram, and the magnitude of these flux density vectors, I show it in this diagram. These are adjusted, these number of turns can be adjusted such that maximum value of Bm, that is also equal to maximum value of Ba. So what will be the net flux density vector that is there in the machine? There are two vectors, stationary vectors, one in this direction, other in this direction. Magnitude of both these flux density vectors are changing according to currents which are flowing in these windings. So what is the net flux density vector? Net flux density vector will be the Phasor sum of these two flux density vectors. So let's see what is the net flux density vector at different time instants. For example, corresponding to this time instant, let's call it omega t equal to 0. What will be flux density vector, net flux density vector? So at this time instant, Ba, what is magnitude of Ba? Magnitude of Ba is 0. What is magnitude of Bm? Magnitude of Bm is maximum but in opposite direction. So here is Bm. Net flux density vector, Phasor sum of Ba and Bm, which is over here. Now let's analyze the situation at this time instant, omega t equal to 90 degrees. What is the situation now? Ba is of maximum magnitude and its direction is upwards. So here is Ba. And what about Bm? Bm at this time instant is 0. So Bm is 0. Net flux density vector at this time instant is equal to this thing, omega t equal to 90 degrees. Next, at this time instant, omega t equal to 180 degrees. Bm has maximum magnitude and its direction is this one, Bm. The same amplitude as this one. This is Bm, and what about Ba? Ba is 0. Net flux density vector, Phasor sum of the two flux density vectors, that is this one. Ba is 0, Bm is this one. That corresponds to omega t equal to 180 degrees. Next time instant, this one, omega t equal to 270 degrees. Bm is 0 and Ba is negative direction with maximum amplitude. So this is the total flux density vector. Bm is 0, Ba is maximum but with negative amplitude, that is in opposite direction. That corresponds to situation omega t equal to 270 degrees. At omega t equal to this time instant which corresponds to 360 degrees, what is the situation? We have Bm in opposite direction, that is the same as this one. So what we see is that the resultant flux density vector, the net flux density vector, is of uniform magnitude and is rotating. Initially it was at this angle, then it rotated to this angle, then further rotation to this angle, in a further rotation. So with this arrangement, what we have achieved is that we have achieved a uniform rotating flux density vector. This situation is exactly the same as that was there in three-phase induction motors. In three-phase induction motors, we had a uniform flux density vector which was rotating. We have achieved the same situation with this arrangement. So therefore, there will be a uniform rotating magnetic field, uniform flux density vector which is rotating, and hence induced torque at start, that will become non-zero, the same as that was there in three-phase induction motors. Hence with this arrangement, the torque speed characteristics are improved. So if there were no auxiliary windings, we had these start speed characteristics for this single phase induction motor. Torque at stationary rotor, induced torque, that was equal to 0, but with this arrangement we have achieved a uniform rotating flux density vector. This similar situation that was there in three-phase induction motors. Hence the starting torque, the torque at 0 speed of the rotor, that will be non-zero. So we have these torque speed characteristics for this induction motor. These are the torque speed characteristics, dotted line, for induction motor with auxiliary winding when we have capacitor over there. What they do is, when this rotor gets started, we can just open this switch, and so as to remove these auxiliary windings from the circuit, and then overall torque speed characteristics will be like this one. And for example, if we open the switch at this time instant, then the torque speed characteristics of this induction motor, single phase induction motor without auxiliary windings. So these are the torque speed characteristics of single phase induction motor when we have capacitor in the circuit up to this point, and then this switch is opened so that we only have these main windings in the circuit. So this blue line, I draw it more thicker so that it is visible. So now the question is, why do we remove this capacitor and these windings from the circuit? Why do we open this switch to remove these windings from the circuit? So the reason is that actually, if we could have uniform rotating magnetic field, that is the best situation, similar to that in three-phase induction motors, which had less vibrations. So why do we remove this switch from the circuit? So the reason is that uniform flux density vector, rotating flux density vector, is achieved under certain conditions. Under the conditions when these two currents are exactly at 90 degrees from each other, firstly. Secondly, the amplitudes of BA and BM are exactly equal. Under these conditions, we shall have a uniform rotating flux density vector. However, these currents IM and IA, these not only depend upon the voltage and inductive reactance and this resistance of these windings, but in addition to that, these currents also depend upon the rotor. It depends upon the rotor and how much load we have connected to the rotor. So the currents in these windings, their magnitude, their phase angles, those depend upon the load which is connected to the rotor. So we can achieve these conditions, these desirable conditions, that is an angle of 90 degrees between these two currents and amplitude of BA and BM to be equal under certain loads only. Under only one load conditions, we cannot achieve that balance under all loads which are connected to the motor. So we can either set the value of this capacitance and this inductive reactance and this resistance of this coil to achieve the balance at one load condition only. So this balance can be either achieved at the starting condition or at the rated condition. If we achieve this balance by setting these capacitance and these parameters to be optimal, we can achieve this condition. If we achieve this balance at the start, we shall have good starting torque. However, performance at the rated load and at the rated speed, that will not be good. And otherwise, we can set this balance at the rated conditions, and then the performance of this motor at the rated condition, that will be very good. However, starting torque will be less. So we can have therefore different variations of these capacitor type windings, we can have these three different situations. We can have capacitor-start motors, which are depicted over here. That is, capacitor is there during the starting, and then these windings are removed from this circuit after this rotor gets started. And we have already sketched the torque speed characteristics of capacitor-start motors, which are depicted over here. Torque speed characteristics of single-phase induction motor without auxiliary windings. Torque speed characteristics of this single-phase induction motors. This single-phase induction motor, when this circuit is in the path, and here the switch, once motor gets started, we can open the switch, and therefore this blue line shows the torque speed characteristics of capacitor-start motors. There is one disadvantage of these motors, that is, we need a switch that will turn on and off depending upon the speed of the motor. That will increase the cost of the motor. The second situation is that we can have capacitor-run motors. In that case, we always have these windings in the circuit, and we do not need a switch. A balance of these flux density vectors is achieved at the rated conditions. So the performance of this motor will be better at rated conditions. However, that balance is not there at the starting conditions. So torque speed characteristics of this motor will be not that much good at the starting. So the starting torque for these motors will be less. So here are torque speed characteristics of capacitor-run motors. These are denoted by this dotted line. Low starting torque, however, performance better than the performance of this motor. And low starting torque, however, cost is reduced because we do not have the switch over here. The third possibility is that we can have capacitor-start and capacitor-run motors. That is, we have two capacitors in the circuit. One capacitor is always there, and the other capacitor is only there during the starting time. So the capacitance of these two capacitors is set such that during starting balance is achieved, so that starting torque is best. And then this capacitor, once the motor gets started, this capacitor is removed from the circuit. Only we have this capacitor, and the capacitance of this capacitor will be such that balance between Vn and Va is achieved at rated conditions. So we have balance both at the rated conditions as well as at the starting condition. And this motor is called capacitor-start, capacitor-run motor. Again, this type of motor is associated with additional cost due to this switch and capacitor. And this has less cost compared to both this arrangement and this arrangement. These motors are generally utilized in home appliances, your fans. These are capacitor-run motors. These motors are utilized where you need a high starting torque, for example in vacuum cleaners and such appliances. And these motors are utilized where you need both better starting torque and better performance at rated conditions. There is another possibility which we call split phase motors. In split phase motors, what is situation? In split phase motors, we do not have any capacitor in the circuit. We have only the auxiliary windings, which can be there throughout the time, or can only be there at the starting. With this arrangement, we cannot achieve an angle of 90 degrees between this current and this current, that is, we shall have this situation. This will be voltage VAC, and this low resistance for these windings, main windings, which will be there in most of the time in the circuit for most of the time. So small resistance means more inductive load, so I will be lagging more, and then this circuit is made up of thin wire, therefore more resistance, more resistive load means this current will be less lagging. So now these two currents are not exactly at an angle of 90 degrees, and therefore the net flux density vector which is there in the motor, that is Bm and Ba, that will not be uniform. However, that will be some rotating flux density vector, and that will also produce some starting torque in the circuit. Once the motor gets started, we can remove these windings from the circuit, because these are associated with additional power losses due to high resistance of this winding. So this type of motor which has low starting torque and low performance at rated condition, this is called split phase windings. These are called split phase windings. The advantage is that we do not need additional capacitor in this circuit. So these are different techniques which can be utilized in single phase induction motor for starting of these motors.